Good morning, students. In our last class, we discussed the temperature dependence on the rate of the reaction. That the rate of the reaction gets nearly doubled when the temperature rises by 10 degrees Celsius. And we found that through the Maxwell distribution of energy curve that for the rise in temperature by 10 degrees Celsius, the molecule or the fraction of the molecules which will undergo the effective collision is going to get doubled. So for the effective collision, there should be the proper orientation and the minimum energy should be possessed by the molecules to form the product, and that energy is known as the threshold energy. Now students, today we are going to do the Arrhenius equation, which give us the quantitative relation between the rate constant, which measures the rate of the reaction, and the activation energy, that is EA. Now what is the activation energy? That is the energy, extra energy which is to be supplied so that the reactant molecules achieves the threshold energy and the products get formed. Now you will see the Arrhenius equation. I'm just going to write down here that K equals to K e raised to power minus EA upon RT. Student, this equation is given by Arrhenius, which give us the quantitative relation between the rate constant and the temperature dependence, right? Because here we are having the T also, right? That is the temperature at which the particular reaction will take place. Now students, here K is denoting the rate constant, and you know that rate constant is the measure of the rate of the reaction. Student, A is here Arrhenius factor or a constant, right? E is here the activation energy, R is a gas constant, and T is the temperature at which the reaction will take place. Temperature at which reaction occurs or it takes place. Now students, we are going to just write this equation, which is the Arrhenius equation, right? Now here one more thing is there, that is exponential term, that is e raised to power minus E upon RT, denotes the fraction of the molecules which will possess the energy, right, greater than the threshold energy, right, so that they can make the effective collision for the product formation. Now students, if we take the natural log on both sides, we will get here ln k equals to ln k minus, it will be EA upon RT. Now students, we know that ln x equals to 2.303 log x, right? So we are going to write it in term of log. So it will become 2.303 log k equals to 2.303 log a minus EA upon RT, right? Now we can write this expression in this form also, that log k equals to log a minus, here it will be EA upon 2.303 RT, right student? So this equation help us to determine the activation energy right? That energy that will be required to get the product formed, right, at a particular temperature. That is log K equals to log A minus EA upon 2.303 RT. Now students, if we just compare this equation log K equals to log A minus E upon RT with the straight line equation, so you can easily plot a graph here. So if you just compare this equation with y equal to mx plus c, so you will plot the graph, right? Now here on the y-axis we will have log k, and in term of the x-axis, what we are going to have, we will have 1 upon t. Here we are not having mx, right? So here it is c, this part is c here, right? So when we plot here, since we are getting it as minus ea upon 2.303 RT, this is negative sign, so the line will be, slope of the line will be in this way, right? So from here we can get the intercept will give us the value of log a, right? This intercept will give us the value of log a, and the slope of this line will give us the value of a upon 2.303 r. So the slope of this line will help us to determine the activation energy for the reaction. Right students, so you will just plot this graph in your notebook. Now students, hope so understood this. Now next we are going to just find out, or we will just frame the two equations, right, at for two different temperature for the same reaction. Now for the same reaction, for the, we can say for the given reaction, at temperature T1 and T2, right? We will write down the expression for K1, log K1 and K2. So at T1, right, we will write it down as log K1 equals to log A, this is Arrhenius factor or a constant, it will remain as constant only, minus EA upon 2.303 R, this is T1. So we have marked it as equation 1. Now similarly at T2 temperature, we will have log K2 equals to log A minus EA upon 2.303 R T2. This will be equation 2, right? Now here in this equation, we are going to subtract equation 1 from equation 2. Now students, it will be in which form? It will be log K2 minus log K1 equals to log A minus EA upon 2.303 R T2 minus it will be log A minus EA upon 2.303 R P1. Now this log A to log A will cancel out, and what we will get? We will get log K2 minus log K1 equals to. So students, here we will get the EA constant. Sorry, we can say the common factor here. EA here it is also there. Here it is also. So from EA common 2.303 and R also common, right? So what you will get here, this is plus minus minus plus, it will become 1 upon T1 minus 1 upon T2. Right students, now we will finally make up the equation. So what it will be? It will be log K2 upon K1 equals to EA upon 2.303 R within bracket 1 upon T1 minus 1 upon T2. Right student? So this is the equation which is being used to determine the activation energy, right, for the given reaction at two different temperature, right? So which indicates that if the temperature changes, right, if we for a given reaction, if we have got two different temperature, definitely the rate constant value will change, right? That is, the rate of the reaction is going to change, and hence the activation energy can just be calculated out, right? Because activation energy is the energy which will be required to just raise the energy of the reactant so that they attain the threshold energy or get the energy equal to the threshold energy, right students? So by knowing the value of temperature T1 and T2, or by knowing the value of K2 and K1, we can determine the activation energy of the reaction.